Hello everyone. This video is on the intermolecular forces that are called London dispersion forces. Okay, London dispersion forces, or LDFs, are very, very weak because they occur between non-dipoles. In other words, they have to be non-polar molecules. Okay, so dipole forces of attraction, hydrogen bonding, those are polar molecules. That's how those relate together. But LDFs apply only to nonpolar molecules, okay? So when let's read this bottom thing. When comparing the properties of molecular compounds, first determine if the molecule is polar. If it is, go to dipole forces / hydrogen bonding. If it's nonpolar, we go to LDFs, okay? So with London dispersion forces, let me see here. With London dispersion forces, electrons, how does it work? Well, what happens is with a nonpolar molecule, electrons go back and forth. Let's just draw like Cl. Electrons will zip back and forth between the two atoms, or perhaps in a big molecule that's nonpolar, evenly. Okay, they're distributed evenly on average. Okay, but something's going to happen. Perhaps it's chance. Perhaps it's an electromagnetic force of attraction or whatever, where it creates a temporary dipole. Whereas this molecule, which is typically nonpolar, now all of a sudden the electrons, for a moment, for an instant, notice I call it an instantaneous dipole, gather to one side, making this side slightly negative and this side slightly positive. Now, for an instant, that's there, and then for an instant, it's gone again, and it's back to this, okay? So you can imagine that the even distribution is definitely something that is highly favored, and the gathering of the electrons to one side is not favored, okay? So we would expect these to be very, very weak, okay? As a matter of fact, London dispersion forces are the weakest of all intermolecular forces of attraction on average. Now, does that mean that some are weak? We can see differences in there, okay? We can see ones that are outliers. So again, this only happens when particles are close together, so we need a close proximity. And the second thing, it sets up something called polarizability, okay? This polar idea behind polarizability doesn't necessarily just apply to London dispersion forces, but it applies to anything. But when we talk about London dispersion forces, polarizability is a big deal, okay? So polarizability is the ease with which the charge distribution can be distorted. In other words, electrons can bunch to one side, making that molecule polarizable, okay? So in general, polarizability increases, the number of electrons increases. So if you take F2, it has a decent amount of polarizability. And as we move down the column all the way to iodine, this is so polarizable with so many electrons. These are, of course, the halogens. It is so polarizable that this is a gas, this is a gas, this is a liquid, and this is actually a solid. It's so polarizable that the London dispersion forces are so strong in this case that it actually forms a solid. Okay, so I'll go over that a little bit in class. Okay, and then molecular weight, in other words, number of electrons, tends to also increase that. So a couple quick statements about the London dispersion forces. They're often the strongest where the intermolecular forces happen between large molecules, in other words, increasing number of electrons. I just showed you that with the halogens. London dispersion forces London dispersion forces, LDFs, increase with increasing contact area between molecules. In other words, the closer they are together, the more you can force them together, the more the London dispersion forces go up. Okay, so in other words, increased pressure. The third bullet point here says London dispersion forces increase with increasing polarizability. In other words, polarizability increases with increasing number of electrons in the molecule. I think I beat that up for the third time already. So let's continue. Okay. Now, when we take a look at this, Cl2 and Br2 have approximately the same shape, but neither is polar. So we have LDFs here. Upon cooling, Cl2 and Br2 form solids. Why? Okay. Now, we can take a look at this and we'll in class, okay? But I want to kind of go into this a little bit. But if you're thinking, you can kind of read the answer there behind some of the stuff. But if you're thinking slower kinetic energy, decreasing the proximity or increasing the contact time, you're right. So here's another example of taking a look at some substances. Of course, we have water. Water is very polarizable. Excuse me, very polar. This is nonpolar. So, and this is somewhere in between. Okay. Probably looks like a polar molecule, but if it is, it's a weakly polar. So the London dispersion forces rank, this has the highest London dispersion forces. This has the lowest. Why? This has the lowest amount of electrons. Okay, this is somewhere in the middle. Now the hydrogen bonds, this has humongous hydrogen bonds because we have oxygen directly bonded to N or F. Okay, that's this case right here. This has no hydrogen bonds, no hydrogen bonds. The dipole-dipole forces ranks, of course, with this being, so I'm talking about the dipole-dipole force rank. With having hydrogen bonds, that's going to be number 1. This is somewhat polar, that's number 2. And this is definitely nonpolar, that's number 3. So taking a look at the heat of vaporization, just check this out all the way to the end. If we take a look at the heat of vaporization, in other words, the amount of heat it takes to melt these things, or vaporize them, excuse me, to vaporize these things, what we're going to do is, you'll notice that this has tremendous amount of heat of vaporization, this not so much, okay? Okay, so in this one, which of the following best explains why ammonia, NH3, has a higher boiling point than methane? Again, you'll see this. It probably has something to do with London dispersion forces versus hydrogen bonding, but there's the correct answer. Again, pause where you think you need to. Which of the following best explains why carbon tetrabromide has a higher boiling point than water? Okay, again, now we're looking at something that is possibly polar versus nonpolar. The correct answer is D. Which of the following would be expected to have the highest heat of vaporization? So in other words, the most energy applied to break the bonds. There we go. Try taking a look at that there. So we're looking for the most polar here. Okay, C. Which of the following would have the lowest boiling point? Okay, so now we're looking for the weakest form of attraction. It's D. Okay, so we'll keep continuing this in class. Again, you can check out some of these things without giving you the answer just yet. Okay, so the next and final topic on intermolecular force of attraction is something called ion-dipole forces of attraction. We've seen these before. This is how something dissolves. So this is all the way back in chapter 4. And you see how the ion-dipole force of attraction is based on several things. First of all, it's based on the size of how polar the molecule is. In this case, water is quite polar. This is the water molecule. It's quite polar, and it's being attracted to something that is ionic. So I'm not going to put these somewhere as far as ranking them, where they lie in like polar, nonpolar, LDFs, hydrogen bonding, anywhere in between. Actually, there's somewhere in between there, but it all depends on what we see and what we're comparing it to. So this is a really helpful slide here. So if you guys want to take a moment to jot this down, I would pause the video here. It's a nice flow chart, so check that out. Okay, and again, we'll take a look in this class. Take a look at this in class. Okay, but basically says the IMFs get stronger, weaker, stays roughly the same in the following molecules. So basically, you can take a look at that there. Pause the video if you need to. And we'll stop there. Okay, if you have any questions, go ahead and email.